So that's how additive mixing works. We start out with colored lights, and we can add those together to get our different colors. We can also have subtractive mixing, which takes away light from our total light. Our subtractive primaries are the opposites or complementary colors of our additive primaries. So the subtractive primaries are cyan, magenta, and yellow. When we add the subtractive primaries together, we produce black. We start out with white light and we take all the light away, taking the cyan, the magenta, and yellow away, and we end up with no color or black, no light left. Here's how that looks. Here we have our cyan, yellow, and magenta colors, and this is also in your book. It shows a little bit better how those mix together. But we can see right there in the middle, when all three of them overlap, we get black. When we have the cyan and magenta mixing together, we get blue. When we have the cyan and yellow mixing together, we have green. And when we have the magenta and yellow mixing together, we have red. Just the opposite of what we saw before. We have our subtractive primaries, our cyan, magenta, and yellow, and the resulting mixtures are red, green, and blue. So again, we can talk about theoretical subtractive primaries, and those are cyan, magenta, and yellow, kind of looking at them the same way we did with the additive theoretical primaries. We can vary the amount of the subtractive primaries from 0 to 100, which results in colors varying between white and that particular primary. The term subtractive is used in this case because light is subtractive through the process of selective absorption of light. So you're taking away certain colors from the total. Cyan subtracts red light, magenta subtracts green light, and yellow subtracts blue light. And that kind of works like we saw in the example with the additive primaries when we started. So when we use our theoretical subtractive primaries, we take cyan plus yellow to give green, which results because red and blue light have been subtracted. We can have cyan plus magenta give us blue. Red and green light have been subtracted. The magenta plus yellow results in red, where the blue and the green light have been subtracted. Finally, magenta plus yellow plus blue gives us black, and in this case, all of the light has been subtracted, so there's none left, so all we have is black. And from your book again, we have the kind of colored graphs that we used before and the square waves that we used before, and we can see that when we have the magenta plus the cyan plus the yellow all pointing towards the center, we end up with a straight line basically at 0, which means no light or black. If we take the yellow plus the cyan, mix them together, we get green at the top. If we take the yellow plus the magenta, we see we end up with the red on the right side there. And finally, we have the magenta plus the cyan gives us blue. So again, just the opposite of what we saw with additive primaries, but if you think about it, they work similar ways as the additive primaries, just going one direction or the other. Let's look at it another way. We can do this by starting out with one white light, which is made up of blue, red, and green components. So that's all the way across the spectrum. So that gives us white light. First we can use a yellow filter to filter out the blue light. Then we can use a cyan filter to filter out the red light. And what's left over is green, because that's the only color that passed through both filters and weren't subtracted out. Here's a picture of how that might work. We start out with our white light with our blue, red, and green components. We put a yellow filter in front of it. The yellow filter filters out the blue, allows the red and green to pass through. And then if we put a cyan filter on our remaining light, it filters out the red and just allows the green to pass through. If there was blue light, it would allow that to pass through also, but the blue has already been subtracted away with the yellow filter, so there's no more present. So the only thing that's left over is the green. So when we have yellow and cyan mixed together, we end up with green. We see that the theoretical subtractive primaries control the amount of light that the visual system responds to in identifiable fashion to the theoretical additive primaries. In both cases, the amount of red, green, and blue light is being controlled, just being controlled in a different manner. That is why the theoretical subtractive primaries are opposite the theoretical additive primaries when placed on a color wheel. And we can look at those primaries on a color wheel like so. We can connect the additive primaries with a triangle, and we can connect the subtractive primaries with a triangle, and we can see how they line up on our color wheel. The green is the complementary color of magenta, blue is complementary color of yellow, and red is the complementary color of cyan. The complementary color of a specific color is the color that lies directly across the circle. So our additive and subtractive mixing systems and the relationships between the additive and subtractive primaries can be more easily understood when we think back and remember how the visual system converts light to color, and by using the theoretical primaries with square wave spectra. If we think back to how our visual system works, remember that we had red, green, and blue sensors in our eyes, our cones. Those cones are stimulated by the colors we see, and then those three, which happen to be our additive primaries, we convert those through our retinal interconnections to our opponent system, like we use with our L, A, and B systems, so that we have a red-green signal, a blue-yellow signal, and a light-dark signal. So those three signals are sent to our brain, and then we interpret those signals as specific colors that come from what our three cone sensors, red, green, and blue, pick up. What about some real systems? Some of the systems we have can be clearly defined as either an additive or a subtractive system. For instance, a cathode ray tube CRT displays are always additive, and paint mixtures are always subtractive. However, many systems use both additive and subtractive mixing in combination. Earlier, we have defined a color model as a mathematical relationship between the input to a coloration system and the output, expressed in colorimetric coordinates. It makes more sense to think about the relationship of the color components and spectra data, or spectral curves, rather than colorimetric data, such as tristimulus values or L, A, and B values. The physics and chemistry of a colorant system are more appropriately expressed in spectral terms. If we use mixing laws that are spectral based, they are always more accurate than mixing laws that were based on colorimetric data. A color mixing law that defines a relationship between color components and spectral data such that the relationship is linear. That's always what we're looking at, that we have a linear relationship. Unfortunately, most color mixing laws, and when we're dealing with color, the relationship between the color components is not usually linear, and we have to somehow mathematically make it as linear as possible. To be a linear relationship, the relationship must be scalable and additive, or must have the components of scalability and additivity. So let's define what those two terms mean. Scalability is the first requirement. Spectral data should be scalable. Changes in the amount of a colorant should only affect the level or amplitude of the spectral curve, not its shape. When we think about working with spectral curves before, the curve can go up and down, but it can't change its shape or move sideways. In a perfectly scalable system where we are able to predict the curves for all levels of a colorant based on knowing the spectral curve at one level. The curve doesn't change its shape depending on how much of it is there. It's always exactly the same shape. Additivity, the other requirement, means that the spectral data of mixtures should be an additive combination of the measurements of the individual components. For example, a measurement of a CRT displays white should be equal to the sum of the individual red, green, and blue channels. There should not be any loss or extra adding in of light. Ideally, the appropriate mixing law would result in a linear system. The main advantage of using a linear system is the use of algebra, and we can mathematically determine what a color's components is made up of. The solving of simultaneous equations are typically used to find colorant levels. When we had our example of our spectral curves several classes ago, where we could tell which colorants are in the mixture by looking at the shape of the curves, we could go one step further in a linear system and calculate exactly how much of each colorant is in that system. Not only what colorants are there, but how much of each colorant. Unfortunately, most often the fundamental spectral measurements must first be transformed in order to achieve linearity. All subtractive systems require this transformation. No natural systems really are naturally linear. Color modeling is an exercise in finding a linear system that will work. And because we're forcing the data that's nonlinear into a linear system, there's always going to be some errors introduced into the system. So far we've talked about additives and subtractive systems. Define a little more specifically subtractive mixing. One such subtractive mixing system is called simple subtractive mixing, and this is mixing that involves the removal of part of a light coming from the source of an object. Simple subtractive mixing involves only absorption without scattering. Examples of a simple subtractive mixing systems are colored filters, colored liquids, and color transparency. In order to evaluate a mixing law, a series of specimens are produced by varying the amount of a single component, usually as a dye. These series are referred to as a tint ladder, a concentration or thickness series, or a color ramp. A set of mixtures can be produced using several colorants in known amounts at several levels. Then instead of varying the amount of colorant in a fixed amount of material, the amount of material or its thickness, if we want to characterize our simple subtractive mixing system, a set of mixtures can be produced using several colorants in known amounts. Then instead of varying the amount of colorant in a fixed amount of material, the amount of material or its thickness is varied so that we can either put several standard thicknesses together to see how they react when you have more of that particular colorant there. Example is a series of colored glasses of different thicknesses, which looks like this. So a single colorant is used to produce a color ramp either by varying the concentration, like we see at the top, so we keep a constant thickness with different concentrations of material in each one, or we vary the thickness like we have on the bottom, but the concentration is the same. So either way, the colorant ramp can be made. Several mathematical relationships have been developed over the years for simple subtractive mixing systems. The Boger-Beer law, Beer's law, and Lambert's law are all relatively simple calculations for simple subtractive mixing system. Here's a graphic that came out of your book that shows there is an exponential relationship between thickness and spectral transmission. So if we start out with 100% of the light and we have 1 centimeter of our particular color and it blocks 50% of the light, if we have 2 centimeters or double the thickness, it reduces the light to 25%, and if we have 3 centimeters or 3 times the thickness, it reduces the amount of light that passes through it to 12.5%. And that's how the relationship of this particular simple subtractive mixing system works. Beer found that changes in concentration also had an exponential effect on transmission. If we had one unit colorant that resulted in 50% transmittance, if we doubled it, we would get 25% transmission. Here is a table that was in your book that shows what the actual mathematical relationship is. It's not something that you'll have to remember or use, but just shows you what the mathematics of the Vogler-Beer law looks like. And if you're really interested in the math to actually calculate concentrations of transparent colorants using this law, there is an example in the Mildmeyer book on page 162. But you'll be glad to hear that you're not required to know how to do the calculation for this course. A couple of weeks ago, we looked at the next type of mixing system, the complex subtractive mixing system, when we looked at the Kubelka-Munk equation. But to kind of review what we talked about there, the complex subtractive mixing system is the most common type of mixing system that we deal with in the real world. In this case, colorants scatter as well as absorb light, and we're dealing with non-transparent pigments. And again, it's described by the Kubelka-Munk. Again, the most common and unfortunately the most complex type of color mixing we experience is that in which colorants scatter as well as absorb light. So we have simultaneously absorption and scattering of light. Both of these quantities must be accounted for in the calculation for a model of this type of mixing to be realistically characterized. These laws are much more complex than for simple subtractive mixing. And to write the equation in an exact form like the Vogler-Beer's law would give equations that are far too complicated for our purposes. We need to simplify our calculations. For most practical purposes, these simplified calculations that are approximately correct, as long as we take in some important assumptions, is the Kubelka-Munk equation. And if you remember from before, those assumptions that are necessary for the Kubelka-Munk equation is that there's enough scattering to completely diffuse the light, so we have an opaque sample. There's no change in the refractive index at the boundary. Calculations must be made at many wavelengths across the spectrum. For this equation to work, we have to do it at a specific wavelength, and it can't be applied to tristimulus values. We apply it to reflectance values. So we need to have our reflectance curve. If you remember from before, this is the actual equation. K over S equals 1 minus R quantity squared divided by 2R, where K is the coefficient of absorption, S is the coefficient of scattering, and R is the reflectance at the specific wavelength that comes from the spectral curve. And if you remember, we used this equation. We didn't have to actually calculate it. We had a table that if we knew R, we could look up K over S in the table, or if we had K over S, we could look up R in the table also. A couple ways that K and S are used when we talk about color formulation programs. In some applications, K and S are separate, so we have to separate them. So we can see the K's are on the top of this equation and the S's are on the bottom, and we multiply the individual K for a given pigment times its concentration, and the individual S for that colorant times its concentration. And then we add that together for all of our concentrations, or all of our colorant. Some applications, the K and S can be thought of as a single value. We have the K over S times the concentration of each colorant in this type of application. Again, if you are really interested in the math, to actually calculate concentrations of opaque colorants using the Kubelka-Munck law, there is an example in the Bill Meyer book on page 166 and 167. And again, you don't need to know how to do those particular calculations, but if you're interested, they are in there. If you remember from what we did before, we can use the Kubelka-Munck equation to compare two colorants, to compare their concentrations, compare strengths, compare economic value. We did a couple examples of economic value, and we can use it for dispersion time evaluations. So there's many uses for the relatively simple Kubelka-Munck equation. And then most color matching software uses some form of the equation to calculate colorant amounts when it predicts formulations. Finally, at the end of Chapter 6, it talks about the different types of matches that we can make when we're in industry. It doesn't really matter how we arrive at that match, either by eye, by instrument and software, or by any combination of the two. There are several types of matches that can be made. It's ultimately up to the customer to decide if the type and closeness of the match is acceptable. So it's always important to understand what the requirements of your customer are so that you can meet those requirements the first time. We have invariant matches, conditional matches, metameric matches. Invariant matches are matches that match under all conditions. And the only way that you can have a truly invariant match is to use the same colorants in exactly the same material. Ideally, that's what you would like. Unfortunately, that's not always possible. Remember when we talked about using the Munsell catalog, for instance, as a standard in the plastics, we found that we can't always use the same colorants. And if we can't use the same colorants, we can't have an invariant match. In an invariant match, we have to have exactly the same curves for the color. And if they're not exactly the same, it's not an invariant match, and we can't have them exactly the same unless they use exactly the same colorants. If we can't have an invariant match, we have what is considered a conditional match. That is a match that only matches under certain specified conditions. For instance, you have a product that is used only outdoors, so you make sure that your match matches under daylight, and you don't worry about the other light source. So what these conditional matches really result from is from metamerism. You can have several different kinds of metameric matches. It could be colorimetric or light source metameric, could be observer metameric, or geometric. Colorimetric means if you have a different light source, you may be able to match under one light source but not under another. Observer metamerism could be visual observers where one person sees it as a match and another person sees it as not a match or not close enough. You can have observer metamerism with people, or it could be instruments where one instrument says that it's within tolerances and another instrument says it's not. So they don't both look at it exactly the same way. Or we can have geometric metamerism, where if we look at the sample in one direction, it looks like it matches, but if we turn it, say 90 degrees, and look at it in a different direction, we no longer have the same color. An everyday example is when you're vacuuming a carpet. Depending on which direction you're going, if you go in two directions in vacuuming, it looks like two places on the same carpet don't match anymore, don't look like the same color. They don't have the same appearance. although they have the same color because they're all made the same way. Sometimes in plastic processes, if there is a high degree of orientation, it may match, for instance, if they're both samples are in the machine direction, but if we have one sample when you're looking at it in the machine direction and the other sample in the transverse direction, they no longer appear to be the same color because of this geometric metamerism. There is a way of actually coming up with numbers, calculating how much metamerism is present. A calculation that's used is called the metamerism index. It can be useful in judging how bad of a metameric situation you have present. In this case, we're doing it in terms of two illuminants. And in our example here, we have, say, daylight and artificial light. It could be any two conditions, really, where we're trying to see how close they are as far as the amount of metamerism is present. So our metamerism index takes our delta L, A, and B values for each of the two conditions and squares it, very similar to our delta E calculation. But here our differences are in, for at least this example, two different light sources. The D is D65 and the A is artificial. And this is really just a general rule of thumb. If we calculate our metamerism index to be less than 0.5, most likely that visually and to most people you wouldn't see a problem as far as metamerism goes in that situation. If the metamerism index is between 0.5 and 1, you need to visually examine the under two illuminants, make your determination that way. It's probably okay, but you better check it to make sure. Finally, if its metamerism index is greater than 1, you better try to reformulate to see if you can lower the metamerism index, because there will be a problem if you need to have a match that is non-metameric for those two particular conditions. Metamerism is something that is a constant problem for color matchers. You need to check your samples visually that way, but this is also a way to have a calculation that can be used to give you an idea how much metamerism could be present in that particular situation.